Hi everyone, welcome back to another video, and in this series we're covering the various ways that the human body sucks. And as we go through these videos, it's important to address the fact that the flaws that I'm pointing out are not related in any way to disease or injury. Rather, these are features of healthy bodies. So the point that many apologists will make is that bodies seem to be awful due to sin and corruption. But this point really doesn't stand because we see evidence of poor design even when the body is functioning at its best. So today's topic is metabolism. It's amazing, right, that animals have the ability to convert glucose into usable energy. But while glucose metabolism is really fascinating to study and it's so incredibly complex, the reality is that human metabolism kind of sucks. And there's some reasons why this sucks. It seems like it's such a great process. We have this input. We're going to put in glucose, and we're going to send the glucose through this incredible process through glycolysis. So we're going to start with glucose. It's going to be converted to pyruvate, which is then going to be converted to acetyl-CoA, which can then enter the Krebs cycle, and then those products can be used in the electron transport chain and produce ATP. And ATP is a form of storable energy in the body, adenosine triphosphate, and you get energy from breaking these three phosphate bonds in the molecule. So it's great that we have this form of usable and storable energy. However, the process that got here is not as simple as what I just wrote out. And in fact, there are steps within this that are incredibly inefficient. And especially when we're talking about the human body in general and evidence for design, the human body in general is incredibly inefficient. And as we cover this first step of why metabolism sucks, and as we go into the next video covering part 2 of why metabolism sucks, the key factor here is inefficiency. So how exactly is this inefficient? Because this seems like a great process, right? And we're going to see some more steps here about why this seems to be amazing. But keep waiting, because this isn't as simple as this seems to be. So we have our input of glucose, we have our output of ATP, but in addition to the ATP that we're going to produce from glycolysis itself, we're going to produce the ATP from the electron transport chain via the transfer of electrons through molecules of NADH and FADH2. So throughout this process, we get a lot of the ATP production due to electron transfer, hence the electron transport chain. And these electrons need to be transferred between multiple different molecules in order to get to where they need to go. And so NAD and FAD are the carrier molecules for these electrons. And so the H, when we're adding on these hydrogen atoms, they are going to be able to carry those valence electrons to the end destination. So this is why we have these molecules. So NADH, for every molecule of NADH that we produce through glycolysis and through the Krebs cycle, we are going to get an additional 3 ATP produced. And similarly with FADH2, for every molecule we produce, we're going to get 2 ATP in addition. So NADH is kind of the VIP here, giving us 3 ATP, while FADH2 still doing a good job, giving us 2 ATP, though not quite as much as NADH. But we're going to see how this plays in, because this is our key factor here. So let's go over to our diagram. So this looks very complicated. I've just added the intermediate steps in glycolysis. We're still going from glucose to pyruvate. And you can see that there's a branching point here in the middle of this pathway that gives us 2 of everything. So that's how we end up with 2 pyruvates. And that's going to be converted to acetyl-CoA. And it's going to enter the Krebs cycle within the mitochondria, which, if you remember from science class, is the powerhouse of the cell. And this is why the ATP production is going to be happening in the mitochondria, while the glucose and glycolysis phase of this happens in the cytosol. So we're going from a cytosolic process to a mitochondrial process, and the electron transport chain is also within the mitochondria. So we have the products from the Krebs cycle that are utilized in the ETC can go straight there from within the mitochondria. So, and then after that, we're going to produce some new ATP. So going through these steps, the first thing that is going to happen is we need to spend ATP. So ATP being the storage of energy, we want more ATP. We're going to spend a couple to make a couple. So we're going to spend some ATP in these first 3 steps. So we're giving up some ATP and we're getting ADP, which still has some energy to it. Not as much as ATP, but it still has 2 phosphates on it. So, still a little bit of energy there. And so if you're thinking that this is the problem that I'm getting to, it is not. We see here that we are losing 2 ATP, but later in glycolysis, we are going to get it back and then some. So down here from these steps of converting 1,3-BPG to 3-PG, we are going to gain back those 2 ATP that were lost in the beginning. And then as we're converting both of our PEP molecules here to pyruvate, we're going to gain another 2 ATP off of this. So we're netting 2 ATP. So we lost 2 and then gained 4. So we netted 2 ATP. This is not the problem that I'm talking about. This is just kind of what happens. But here, the next thing that is going to happen is we are going to produce 2 NADH molecules. So we're going to have NAD plus is going to come in between the step of G3P and 1,3-BPG. We're going to produce 2 molecules of NADH. So if you remember looking back at the other picture, for every molecule of NADH, we're going to produce 3 ATP down the line. So cool. We're about to make some money here. We're about to get some more ATP. And in the Krebs cycle, we're also going to produce some NADH. And we're also going to produce some FADH2. And these are going to go straight to the electron transport chain to convert to ATP. And so we get, for each of these 3 NADHs here in the Krebs cycle, we're going to get 3 ATP here. So we get 9 ATP from these, and then our FADH2 here is going to give us 2. So we're still getting a good amount of ATP from these in the Krebs cycle. And then we have these 2 NADH here, which have still yet to be used. So, right, this seems very simple. All we need to do is take these NADH, move them to the mitochondria, and then bang, we get 6 ATP right off the bat there because we get 3 ATP per NADH, right? So that should get us another 6 ATP, right? So we just move these NADH to the mitochondria and we produce it. No, that's too easy. We can't do that. Because NADH is not permeable through the mitochondrial membrane. So this is a problem. We cannot move NADH from the cytosol to the mitochondria. So while these NADH and FADH2 molecules in the mitochondria can, right off the Krebs cycle, go into the ETC and produce ATP, we cannot do that with cytosolic NADH. So what do we do? Well, we're going to have to take some extra steps here. So instead of having a straight shot to some ATP production, we have to utilize some shuttle systems. So instead of making this easy and being able to just cross membranes, we have to, number 1, produce more enzymes in the cell. So we have to use some ATP to produce enzymes to make these shuttles work. But the shuttles in themselves add a complicating step to this whole process. So the malate aspartate shuttle and the glycerol phosphate shuttle utilize, as it says in the names, either malate or an aspartate to transfer electrons from NADH to the mitochondria, or we can use glycerol and phosphate to do kind of the same thing. So it's going to basically, if we take the malate aspartate shuttle first, we are going to take these NADHs. It's going to go to the malate aspartate shuttle. It's going to drop off these electrons to the malate, and then it's going to once again be converted to NAD+, go back through the cycle. But as we drop off our electrons here at the malate aspartate shuttle, it's going to pass those off to an NAD+ in the mitochondria, and so it's going to become NADH and then go to the electron transport chain. Okay, so pretty simple. This is one extra step. We didn't lose anything with this one, right? So our NADH simply transferred to a different NADH and then went to the ETC. So no biggie. This was an equivalent exchange within this process. So we had, if we use the malate aspartate shuttle, we had NADH in the cytosol. We simply converted that to NAD+, moved our electrons over to NADH in the mitochondria. So similar molecules. We didn't change the identity of the molecules there. We still net our 3 ATP, right? Because these are equivalent. And most cells are going to use this equal exchange shuttle. So most of the cells in our body are going to utilize this very efficient mechanism. However, not all cells can do this. So some cells, including the brain and skeletal muscle, so 2 types of cells that require a significant amount of energy, a significant amount of ATP to be used, are going to use the glycerol phosphate shuttle, which is less efficient. This is inefficient of a shuttle. And the reason is because instead of transferring cytosolic NADH to mitochondrial NADH, what it's going to do is it's going to transfer NADH to FADH2. And then that FADH2 is what is going to donate the electrons to the ETC and then produce the ATP. So look back at our picture, right? So our FADH2 can only generate 2 ATP from that molecule. So we had, in the cytosol, we had NADH. So we should be getting 3 ATP. But instead of that, we are going from NADH to FADH2. So we are only gaining 2 ATP when we should have gotten 3. And this is, again, in the brain and the skeletal muscle. We need a lot of ATP to be working here. And it doesn't seem like much difference, right? 3 ATP versus 2 ATP isn't much of a difference. But imagine if you took $1 out of a cash register every day or even every few minutes. It doesn't seem like much. You're only missing $1. But over time, that adds up because this is per glucose, right? So you're losing, even if you're using both of your NADH that you produced from glycolysis, remember, you produce 2 of these. If both of them go to the glycerol phosphate shuttle, you're losing then 2 ATP off that process. And if you lose 2 ATP for every glucose molecule that you are burning, and you do the same process thousands of times a day, it's going to add up and you're going to lose a significant amount of ATP. Why would you want to generate fewer ATP when you could have more, especially in the brain? It does not make sense. It's inefficient, but this is the way that it works. So when people say that humans are designed How come we were built with this inefficiency in areas that need it the most? We are spending the same amount of resources and we're using the same amount of input, but we're getting less ATP for the exact same amount of input. So, is this a well thought out process? I don't really think it is. It's good enough. And something that people like to misquote about evolution is that evolution is supposedly, in their eyes, supposed to make something better and improve. But that isn't the case. Evolution simply selects for what works. And this works. It does. I'm not saying that it doesn't. But it does not work as well as it should if this were to be designed. If this was designed, you'd probably see all of these NADH converting to 3 ATP, but we do not see that. So, again, I don't see why this process necessitates intelligent design, and I don't think you should either. And this is only one step in the human metabolism process that I'm addressing today. I still have another video going into the electron transport chain and how incredibly inefficient the ETC is. So I hope that you stick with me in the next video. And the human body sucks. I'll see you all in the next one.